Hey, hello and welcome back, everybody. Moving on to the subsection, we'll be covering spherical and cylindrical coordinates today. You've probably heard in the ether spherical and or cylindrical coordinates thrown around as pretty common multivariable calculus topics, and we're finally here. So spherical, what do we want to think about these coordinates? Well, they're coordinates just like polar coordinates. You can think of polar coordinates as circular. All right, polar coordinates are kind of based off the circle, really concentric circles, and then angles within those concentric circles. Spherical coordinates is going to be similar, but in higher dimensions. So technically, my version of spherical coordinates, we're going to see this right away, can start out in an arbitrary number of dimensions, but in reality, we're thinking about spherical coordinates in 3 dimensions. So what would concentric spheres look like? We'll just draw a sphere here, and then maybe a bigger sphere around it. Then maybe a bigger sphere around that one. Of course, they start to look pretty ugly when you're in 3 dimensions and you're trying to draw things. Really, the screen is 2-dimensional, so I'm trying to draw concentric sort of 3-dimensional spheres embedded in 2 dimensions, but hopefully you get the idea. So there's a lot of concentric spheres there, and then we will still have kind of angles radiating out from these axes. There's going to be angles radiating out from the xy plane, and there's also, because we've added a dimension, there's actually angles that are radiating downwards from the z-axis is the way we want to think about spherical coordinates, is that the angles can radiate in different directions. We will see what that looks like in a bit. For now, I'm just going to define these, and this looks pretty atrocious for now. I included them in arbitrarily many dimensions just because it's something that has actually shown up in my mathematical career, so I wanted to throw it out there as something that's possible. You can certainly define spherical coordinates for any number of dimensions of a sphere, and they're going to look more or less the same as what we see when we reduce down to 3 dimensions. What's going to happen here is the point of spherical coordinates is to reduce everything to the magnitude of kind of the vector which comprises all of the entries in the argument of whatever multidimensional function you have. So here we have just the square root of all of the entries squared. In other words, this is like the magnitude of the vector x, but this is going to play the role of r, which we'll call the radius, right? Because it serves as the radius from the origin out to some sphere. It's serving as the radius for the size of that sphere. The distance to the origin is equal to the radius for anything on the surface of a sphere. So that's always going to be the first entry in the output of spherical coordinates. And then the rest of these entries just start being different angles. Remember how I said there's going to be a lot of angles sitting around? Basically what happens is you basically peel off, here I'm peeling off xn, the very last term, you peel that off, and you kind of say, hey, I'm going to compute the angle, this is the angle away from xn, whatever that xn coordinate is. It's going to be the angle away from xn, and then you can kind of peel the next term off, xn minus 1, and you get, in the second case, this is the angle away from the xn minus 1. And when I say away from these things, these are the axes, right? So the axes that refer to each of those variables. You keep peeling off, so this is the angle away from the xn minus 2 axis, and this goes all the way down until we get the the angle away from the x3 axis. And then you'll notice that when we get to this very last term, you only have 2 axes left. You only have the x2 and the x1 axis, and so this is actually the angle within the plane comprised of x1 and x2. Okay, so that's going to be the angle within the plane comprised of 2 of them. So you have all these large collection of angles away, and then your very last angle is actually the angle within. Okay, so there's one special angle at the end, and we'll see this in the way we label these. So there's a lot of angles away, but there's one angle within an actual plane, as well as the radius up front. Okay, so we give the radius, obviously, the name r. What name do we give all these angles? Well, we give them the names phi1, phi2, all the way to phi n minus 2. It's a little annoying that the subscript on phi does not agree with the subscript on the these axes that the angles describe their awayness from. I guess if you wanted to reindex, you could force them to agree. That's totally fine. Nothing's crazy there. But this final angle, we give a new name. That one's the angle theta, and that's the one that's within the x1, x2 axis. And so we of course call r the radius. We call each of the phis, right? Each of these special angles away from an axis. We call those the polar angles. And why do we call them polar? Well, if I draw my 3-dimensional grid again, let's think about if I put a globe on this 3-dimensional grid, just like an Earth globe, right? I put a globe on here, then the poles of the Earth are up here at the top or down there at the bottom, right? The north and the south pole. And it turns out when we do our spherical coordinates away from an axis, or there's going to be some angle away from that axis, that positive z-axis, that's going to be one of my phis. That's going to be the angle away from the z pole, right? It's that pole right in the middle, and phi is the angle away from the pole. That's why we call it a polar angle. Meanwhile, why do we call theta the azimuth? Well, the azimuth is exactly the same name that we gave to the polar angle theta, and that was the angle within the xy plane. So we're going to see the azimuth as kind of this angle that rotates us through the xy plane. So theta is in the xy plane. Okay, and of course, just like with other coordinate transformations, the inverse transformation is just as important as the forward transformation. And the inverse transformation here, every single term is going to have a radius inside of it. But then what does the rest of each piece look like? Well, you take the cosine of each of those polar angles. So it's the cosine of each polar angle is kind of the final term in the list of a multiplication. And then everything else, all the other previous angles, have sines of the previous angles inside of them. And remember, this is only in arbitrarily many dimensions. So eventually we'll see this in 3 dimensions, which is what you'll have to focus on for all of the exercises. Just wanted to show you that it's possible to do in any number of dimensions. The very last case is special. This one's special here. And because we switch between, these were all the polar angles, we switch between the polar angles over to the azimuth, then we flip from having a cosine at the end, we just pick up a sine at the end. So everything else is the same. On the very last term, you have sines of all the previous polar angles, but because we're working with the azimuth right at the end, we have to use the sine of the azimuth. That just works out for us. And of course, the inverse function is giving us the variables x1 through xn, as we would expect the inverse to do. There's a volume form associated to these spherical coordinates, right? Let's take the determinant of the derivative of your inverse transform. This would be of r of phi1, of phi2, of phi n minus 2, and of theta. It's always the determinant of the derivative of the inverse transform that gives you the multiplicative term in the volume form. And since we know what the inverse is, we were just looking at the inverse. If you go through the work, I've saved it as one of these master exercises. If you go through the work of computing that determinant of that derivative, you end up with r to the n minus 1. Remember, n is the number of dimensions we're in. R to the n minus 1 sine n minus 2 phi 1 sine n minus 3 phi 2 all the way down sine 2 phi n minus 3 sine phi n minus 2. So really, these are all of the polar angles. Notice the azimuthal angle does not show up in here, so there's no multiplicative theta. But we do have all of these polar angles with reducing powers of sines. So that's really what that multiplicative term is in spherical coordinates. And from this point onwards, we're going to jump to dimensions 2 and 3, because those are the ones that are going to be both the easiest to work with, but also the most useful in terms of applications. The real world is 3-dimensional. Computer screens are 2-dimensional. Maps are 2-dimensional, et cetera, et cetera. Well, 2-dimensional, you already know. This proposition says 2-dimensional spherical coordinates are polar coordinates. Not really a surprise. The 2-dimensional sphere is the circle, and if we set polar coordinates as circular coordinates, they're basically the same thing, right? So what do we have? We have, if we just look at what phi looked like in terms of polar coordinates, of course, there's a radius, which is exactly the polar coordinates radius, and we have a tan 2 show up, y comma x. Technically, these are flipped compared to my previous definition of generalized spherical coordinates, but it doesn't really matter which one you decide to be your axis that you're considering everything as angles away from. We like to think of the positive x-axis as the one we take angles away from, so we flipped them around. But yes, the polar coordinates are the 2-dimensional spherical coordinates. And of course, everything agrees. Our inverse is exactly just r cosine theta, r sine theta, and our volume form picks up an r, which we saw in the last video. Because if I just scroll up really quick, notice if I put a 2 in there, a 2 in there, and actually none of the rest of these angles exist. And in fact, actually this angle doesn't even exist either, so none of these exist. We just put a 2 in for r, that's r to the 2 minus 1. Of course, that's just r. So in 2 dimensions, you just pick up r as your multiplicative term. And now we'll move up to 3 dimensions. So what do spherical coordinates really mean? This is the one that everybody's going to expect you to use exiting multivariable calculus, is the 3-dimensional spherical coordinates. What do they look like? Well, they look like our coordinate transform, which gives me a radius, and the radius is just going to be root x squared plus y squared plus z squared. So this is r. It's going to give me theta, and now I've exchanged the order of theta versus phi. That's a little bit annoying, but that is convention. So that's going to be theta, which is going to be the angle within the xy plane. And then our third output is a tan 2 of, now this is basically a radius, what's going on here? This is really a radius within the xy plane, right? It's like your special xy radius. And then you've got z over here as the second entry in atan 2 there at the end. This is going to be phi, and this is going to be the angle away from the positive z-axis. Okay, the angle away from the positive z-axis is going to be this last term. So you've got the angle within the xy plane, the radius, and then the angle away from the positive z-axis. That's going to be the polar coordinate system. We, of course, still call theta the azimuth and phi the polar angle. So we're going to look at the inverses now. The inverse of spherical coordinates, inverse coordinate transformation, is going to be r cosine theta sine phi. This is what gives me x. We have r sine theta sine phi. This is what gives me y. And we have r cosine phi. This is what gives me z. It's pretty useful just to memorize each of these the same way you probably memorize for polar coordinates, r cosine theta and r sine theta. And what's really nice here is that those have survived, right? So x and y both have the kind of the polar coordinates, r cosine theta and r sine theta inside of them. It's just in 3 dimensions because we're spherical. We're paying the price of a sine phi to kind of account for the fact that there's another angle between the z-axis, and then z will pick up a cosine of phi. So that's the forward and inverse transform for spherical coordinates. And now we'll start this remark because you've probably noticed that I keep switching the order of variables around, and that gets very confusing. It's very annoying. There's nothing I can do about it. There's so many different conventions for coordinate labels. Conventions, I mean like definitions that different subdisciplines of mathematics and physics use. So you're just going to see so many different versions of spherical, the order of variables, the symbols used for variables in spherical coordinates, even in polar coordinates, and even we'll see in cylindrical coordinates too. So it gets quite confusing. Something that's already shown up kind of in the last video with polar coordinates is that I was using negative pi to pi a lot, but I was also using 0 to 2 pi a lot. And I was just doing that myself as like a mathematician who tries to stay consistent when I'm writing things down. Even I, can't perfectly stay consistent. I swap between a theta range of minus pi to pi and a theta range of 0 to 2 pi. So like, if I can't even keep it straight, most people aren't keeping it straight. The thing is that the results you get are still correct. You're still getting, it's still describing an entire circle's worth of rotations, and all the computations you do are still correct. It's just kind of annoying that some people use one and some people use the other. And what's even more annoying is that mathematicians, so this is what I've presented, will use theta for the azimuth. And remember, the azimuth is this xy plane angle. And mathematicians will use phi for the polar angle, and recall that's the angle away from the z-axis. But physicists turn around and they say, no, thank you. I would like to exchange the two of those. They're going to use theta for the polar angle, and they're going to use phi for the azimuth. And both of us use the ordering r, theta, phi. So the physicists, the ordering is the same symbolically, but they put physicists, or let's say physicists, put the polar angle here. But they still use theta as the symbol, and physicists will put the azimuth here, and they'll still use phi as the azimuth symbol. So it's just incredibly confusing when you read different texts between different disciplines. Everything in the applied sciences usually follows the physics perspective because physics kind of grounds all of the applied sciences. Somebody made the decision back in the day and it stuck for both physics and both math, and they just didn't agree back in the day, and then by the time people figured out that they don't agree, we were already stuck with it. So I'm very sorry, but we're going to use the math convention in this book, and please just be aware that the physics convention exists and that, different conventions for angles exist. And to add salt to the wound, there's different versions of each of these symbols. So sometimes instead of R, you'll see this, which looks like a P. This is actually the Greek letter rho, which, is the Greek R. That's why it says, rho, the first consonant sounded rho is an R. It says Greek letter rho, even though it looks like a P. That'll be used to mean radius quite often, so you'll see that sitting around in spherical coordinates. There's a variant version of theta, which looks like this weird script V, but it's not. It's actually theta. Sometimes you'll see that. I've seen a lot of European texts use the variant of theta. And then you've already seen the variant of phi, of course, which is like the other version of phi. So there's 2 versions of phi, there's 2 versions of theta, and sometimes R gets swapped for rho. I'm really sorry, but I decided it was more important that I show you that all these things could be either than just confuse you the first time you see it in a different way. I'm going to try my best to be consistent in this book, but even I will have some slip-ups now and then. Probably not in the book, but I'll have some slip-ups maybe other times. Let's look at the spherical coordinate transformations here. I've got a couple points. My point 3/2 or root 3 over 2, 1. Currently we're working in the Cartesian plane. Here's my x, y, and z axis. I'm going to go out 3/2 in the x direction. I'm going to go out root 3 over 2 in the y direction, and go up 1 in the z direction, and then wherever I end up is exactly that point. You've been doing this the whole semester. I can do 3 root 6 over 4 and negative 3 root 6 over 4 and negative 3 halves as, okay, 3 root 6 over 4 in the x direction, negative 3 root 6 over 4 in the y direction, then down negative 3 halves in the z direction, and then you end up down there as your point. And then here we have the point negative 5 root 2 over 4, negative 5 root 2 over 4, comma 0. So we go negative 5 root 2 over 4 in the x direction, negative 5 root 2 over 4 in the y direction, and nowhere in the z direction, and then wherever I end up is my point. Not too special there. Like I said, you've been doing that the whole time. But let's go ahead and perform the spherical coordinate transformation on these points. And recall how we do that. Well, for the point 3 halves root 3 over 2, 1, we're going to take, for the radius, the square root of each of the terms squared and added together. That's eventually going to give me a 2. For the azimuthal angle, right, for theta, we're going to take the 2-argument arctangent function, a tan 2, and we're just going to work on the xy coordinates. So we're just going to do a tan 2 on the xy coordinates. Don't forget a tan 2 likes to swap y and x around. We're going to put root 3 over 2 there and 3 halves there, and that's going to give us an angle, if we compute it out, an angle of pi over 6. And then finally, we're going to compute the a tan 2 of, keep this in mind, it's right, this is kind of the xy radius, right? The xy radius, so x squared plus y squared underneath the square root there, and then that's compared to the value for z being this 1 underneath a tan 2. If you just plug that into a calculator, what do you get? You get pi over 3 for the third output. So in spherical coordinates, this point 3 halves root 3 over 2, 1 is actually going to be written as 2 for radius, pi over 6 for theta, and pi over 3 for phi. We do the same thing with the other points. So my point 3 root 6 over 4, negative 3 root 6 over 4, negative 3 halves. You just square each term and then add them together and take the square root for r. In this case, that gives me r equals 3. You take a tan 2 of the y entry and then the x entry. For theta, that gives you negative pi over 4 here. Then you take a tan 2 of the square root of the x entry squared plus the y entry squared, and then that's against the z entry. That's going to give you 2 pi over 4. And then for the last point, negative 5 root 2 over 4, negative 5 root 2 over 4 comes to 0. We, of course, find the radius by squaring each entry and then computing the square root. We find the azimuthal angle by taking arctangent of the y entry and then the x entry. Then we find the polar angle by taking a tan 2 of kind of the xy radius here. There's my x term squared, my y term squared, and then a square root, all against the z value. And what these reduce to is the radius of 5 halves. Really, for the azimuthal angle, we have arctangent of negative 1, negative 1, which would be negative 3 pi over 4. And for the polar angle, and this is a slight typo here, that should be positive. For the polar angle, for a tan 2 of 1 comma 0, you just get pi over 2. If we plot all of these, let's think about what it means to actually plot them really quick. So I've tried to do my best to draw a few concentric spheres there, give us an idea of how to plot all of these. What are we doing for something like 2 comma pi over 6 comma pi over 3? Well, the 2, we're going to go out in the radial direction 2 units, so we're going to go out to 2. And then that pi over 6 in the middle, that's referring to me moving in the xy plane by an amount pi over 6. So that's that tiny little angle right there. That's going to be a pi over 6 amount. And then what's the pi over 3 referring to? Pi over 3 refers to away from the z-axis, right? The positive z-axis is up top. I'm going to go down by pi over 3 away from that z-axis. So in some sense, what I'm doing is going out 2 units and then over by pi over 6 units, but then I don't really go up from the xy plane. I actually have to come back down from the positive z-axis, that last pi over 3, and that's how I get to my final point here. And then for the next point, which is 3, negative pi over 4, and 2 pi over 3, we do something similar, right? We're going to go out 3 units, and then we go negative pi over 4 in the xy plane, so that pulls me out here, negative pi over 4 within the xy plane. And then what's 2 pi over 3? Well, I actually have to come up from this z-axis, the positive z-axis, all the way down an angle of 2 pi over 3, all the way down from the positive z-axis, and that's what gets me down there below the xy plane. And then for my third point over here, 5 halves, negative 3 pi over 4, and pi over 2, what am I doing? Well, I'm going out 5 halves, which takes me out there, and then negative 3 pi over 4 is bringing me all the way around within the xy plane. So negative 3 pi over 4 within the xy plane, and then that pi over 2 says, hey, I'm going to start on this z-axis and move down by pi over 2, which is a quarter turn, right? So this is a pi over 2 away from the positive z-axis, and that's how we get to the point at the end there. It's really not too complicated if you do them piece by piece, right? Think about going out a radius and then around the xy plane and then down from the z-axis to get where you need to go. And of course, if we compare this back to those 3 points, the first 3 we had, think about where the red one is, where the blue one is, and where the green one is. Turns out they're actually geometrically equivalent, right? This is what's important about coordinate transformations, is that all 3 of these points are geometrically in the same locations, even though we're representing them with different numbers. Of course, if we look at the volume form, we had that earlier proposition that told me about volume forms for any number of dimensions of spherical coordinates. If I reduce myself to the 3-dimensional spherical coordinates, my volume form becomes r squared sine of phi. Okay, so I'm going to have to multiply by r squared sine of phi if I'm integrating in spherical coordinates. So let's actually look at integrating in these coordinates. We already saw how coordinate transformations could make integrals easier in the last video, and the same thing holds for spherical. It's just a very specific choice of coordinate transformations that makes your life easy. Let's look at this ice cream cone that I've developed here. Here's an ice cream cone. It's described by the set, or the domain omega, where z is bounded below by root x squared plus y squared and above by root 9 minus x squared plus y squared. So that's the ice cream cone. How could we find the volume of such an ice cream cone? Well, you might be tempted to just do the volume by getting a cone on the bottom here, right? And then saying that that top half is just a hemisphere, but this top half actually is not a hemisphere because it's actually a portion of a much larger sphere that kind of comes around like this. So there's actually a larger sphere happening here to construct the top half of this cone. It's not simply a hemisphere, so that top half does get a little tricky if we don't have spherical coordinates at hand. So how are we going to actually produce the volume of this ice cream cone? Well, we're going to have to make the coordinate transformation into spherical. So let's recall in spherical, we have that x is r cosine theta sine phi, y is r sine theta sine phi, and z is r cosine phi. All I'm going to do is I'm going to take this domain, I'm going to replace x with r cosine theta sine phi, y with r sine theta sine phi, and z with r cosine phi, and then see what we get. And I know it looks intimidating, but really I'm just replacing, there's my x replaced with r cosine theta sine phi, here's my y replaced with r sine theta sine phi, there's z replaced with r cosine phi, there's the x replaced with r cosine theta sine phi, here's the y replaced with r sine theta sine phi. So I've just replaced every x, y, and z with, you know, their versions in spherical coordinates. And actually my life gets pretty easy now because a lot of Pythagorean identities show up. You've got a cosine squared here plus sine squared here, so that's just going to get reduced to an r squared sine squared on that side. We also have a cosine squared here and a sine squared here, so it's going to be r squared sine squared phi on that side. And now notice I've got a square root on both sides here. I could go ahead and square everything to just get r squared sine squared is less than r squared cosine squared is less than 9 minus r squared sine squared. And if I want to simplify this a little bit more, what could I do is I could actually take this negative r squared sine squared and add it to every term. So I'm going to add it to the middle term and add it to the left term. That's just going to give me 2 copies of the left term, and it's going to give me yet another Pythagorean identity in the middle term, and all that's going to be remaining in the last term is going to be a 9. And so we just keep manipulating these inequalities down, right? The Pythagorean theorem is going to reduce that middle term to just r squared. And then what do we see we have? Well, you could interpret either of these two as really the final setting that we're going to have to deal with to recover a normal domain, right? Currently, it's not written in the language of a normal domain, but you can tell it's pretty close, right? Because we actually have r just bounded by a constant, at least on one side. On the other side, it's not quite bounded by a constant, so we'll have to figure out what's going on there. But it's certainly upper bounded by the constant 3. So let's just focus on this lower inequality here, since that's the one that's not currently written as a normal domain. What can we do? Well, if we just focus on that, we see that both sides have an r in them. We could cancel those r's out, and we bring the root 2 over to the right-hand side. We see that this is just telling us that sine of phi needs to be less than 1 over root 2. And if we think about our unit circle, where's 1 over root 2 for sine? Well, that's right up here. Right? This is 1 over root 2 for cosine and 1 over root 2 for sine. Where's sine? Where's the y value less than 1 over root 2? It's just going to be right here. I mean, technically, it's everywhere that's negative, including over there. But if we remember that phi, right? Phi is the angle from the z-axis and can only take values between 0 and pi, so the only values that phi can take are between 0 and pi. Well, then the only values that this unit circle can satisfy are just going to be that little section on the right-hand side. So it's this little section right here that we see for phi, or in other words, phi is going to be between 0 and pi over 4. So that's actually what that lower bound told us. And now, if you use the upper bound, that r was bounded above by 3, we see that r is just going to be somewhere between 0 and 3, if phi is going to be somewhere between 0 and pi over 4. Now, if we actually go back to the image, you could get there from the image too, because what's going on in this image, let's think about it. Here, r is going to extend out away from the center, right? It's a radius, so it extends radially out from the center. What is this distance? This is a distance of 3, and in fact, in every direction, this is a distance of 3. So we've got these distances of 3 for r, and even at the top here, that's also a distance of 3. The image is a little bit skewed, so it looks like the top's actually taller than the sides. But everything here is actually a distance of 3, and so you see that the radius, the smallest value of the radius could possibly be is 0, and then the tallest value of the radius could possibly be is 3. And then in terms of phi, remember phi is like the angle away from the positive z-axis. What is this angle? Well, that's just the angle at the bottom here, and you could use just a little bit of trigonometry to tell you that that angle needs to be pi over 4. So of course it starts at 0 and it ends at pi over 4. That's what we saw purely algebraically below here, is that phi is between 0 and pi over 4. So all we're going to do to find this volume then is we're just going to integrate the region with respect to the volume form. And the volume form in spherical, right, the spherical volume form has r squared sine phi inside of it. So we have to pay that price of r squared sine phi, but we do just have our normal domain up here. Normal domain, r is between 0 and 3, phi is between 0 and pi over 4. What about theta? Well, theta is always between negative pi and pi, or as I often like to write in my integrals instead, 0 to 2 pi, right? Theta can take these values. That's just one complete revolution around the xy plane. Why is that the case up here as well? We can kind of see it. There's one complete revolution in the xy plane directionality of the xy plane. That revolution is theta, which is why you can get away with something like 0 to 2 pi, or we can similarly get away with, negative pi to pi. Either one is totally fine for theta. So we're going to integrate all these, and when I integrate r squared, of course I get r cubed over 3. That's going to give me a 9 on the bounds. When I integrate sine of phi, I'm going to get negative cosine of phi, which is going to give me really a 1 over root 2 and a 1 on the bounds. So if I simplify everything, including my 2 pi from theta, I get 9 pi 2 minus root 2 as the volume of this ice cream cone. Kind of surprising that we were able to find the volume of the ice cream cone. Very cool that we can do it in spherical. So we have one more example in spherical, and then we'll move over to cylindrical. So we've got another case of maybe something I want to integrate. Here's a function which I'm defining as 1 minus root x squared plus y squared plus z squared. Of course, light bulbs should be flashing. That's really just r sitting in there. And especially we have this domain omega as well, which looks like x squared plus y squared plus z squared is less than 9, y is positive and z is positive. It looks like r squared there, so more light bulbs should be flashing. That probably we want to convert this to spherical coordinates. So let's see if we can compute the integral, right? What do we actually want to do? We want to integrate the function f over the domain omega. Let's see if we can do that by computing spherical coordinates here. Well, really quickly, we do just recover that f as a spherical function is just written as 1 minus r, and we can convert omega into spherical coordinates by realizing what I've already mentioned, this x squared plus y squared plus z squared is going to be r squared. What do we do with y and z? Well, we just remember that, the y coordinate with regards to spherical variables is r sine theta sine phi, so I'm replacing the y coordinate with r sine theta sine phi, and then the z coordinate with respect to spherical variables is r cosine phi, so I'm replacing z with r cosine phi. Now we're almost there for a bound on the radius, right? We just take a square root. We see that the radius is bounded by 3. We do have to put a little bit of extra work into these two terms to figure out some normal domain bounds for theta and phi. So what should we do there? Well, we're going to isolate. Let's just isolate this last one first. We know that the radius is always positive. So something like r cosine theta being positive, we don't really care about r, and we can just say cosine phi should be positive. Well, what would cosine phi be positive mean? Let's look at our unit circle. And phi is only allowed to be between 0 and pi. Where is the x value? Because cosine is the x value. Where's the x value positive? That's in this section. And so we see that phi has to be between 0 and pi over 2. It's just that section. And we do the same thing with this other inequality. Because this other inequality is going to become, well, either r is greater than 0, but that's always the case, or maybe sine of phi is greater than 0. But notice that this region that I've already decided phi was in, that the y values are always positive as well. So that's already satisfied. So both r greater than 0 and sine phi greater than 0 are still already satisfied. We're only going to care about sine theta being positive to keep that inequality true. And where would sine of theta be positive? Well, that's also like the unit circle, where sine positive on the unit circle. And because it's theta, theta is allowed to take all the values on the unit circle, but sine, the y value is only positive on the top half. So you get that theta is between 0 and pi. So altogether, we've discovered that these three inequalities are telling us that r is less than 3, that phi is between 0 and pi over 2, and that theta is between 0 and pi. So my domain as a normal domain looks like this one, r between 0 and 3, theta between 0 and pi, phi between 0 and pi over 2. Which means if I want to integrate my function, this function, 1 minus r, if I want to integrate it over the domain omega with respect to spherical coordinates, I have my function 1 minus r, but then this is my volume form, right? I still need to include the volume form in spherical coordinates, which will be r squared sine phi. And then I need to include my normal domain bounds. Well, r goes between 0 and 3, theta goes between 0 and pi, and phi goes between 0 and pi over 2, according to omega. And then from that point onwards, I'm just going to distribute r I get r squared minus r cubed. I integrate in r. I plug in my values for r. That happens to give me a negative 45 over 4. I can integrate in theta, but there's really no thetas in my integrand right now, so I just pick up a theta for free. Theta goes from 0 to pi. That's just going to give me a pi in my coefficient. And then finally, I'm going to integrate in phi, so I'm integrating negative sign. I'm going to get a positive cosine phi from 0 to pi over 2. That's going to give me negative 45 pi over 4. That gives you enough examples, hopefully, of the spherical coordinate systems. I feel like you can handle some problems with those. Let's hop over to the cylindrical coordinates. And really, I don't think these are too hard to tackle once you've handled both polar and spherical coordinates. So what happens with cylindrical coordinates is that these are coordinate systems in which I'm going to take any subset of 2 of x, y, or z and replace them with polar coordinates. So for example, I could take the subset y, z and replace those with polar coordinates, or I could take the subset x, z and replace those with polar coordinates, or I could take the subset x, y and replace those with polar coordinates. And then, of course, the remaining case just come along for the ride. So in the first case, the variable x was not included in the polar coordinates, so it comes along for the ride. In the second case, y wasn't included in the polar coordinates, so it comes along for the ride. And in the third case, z was not included in the polar coordinates, so it comes along for the ride. So any of these cases are considered cylindrical coordinates. Why are they considered cylindrical? Well, it's because if you take x and you keep it the same, that means I'm keeping my x-axis fixed, and then I look at r and theta, these create circles around that axis. You can imagine if I take my axis and I put a bunch of circles around it, you know, really polar coordinates, so radially larger circles around it. What have I actually constructed? Well, I've constructed a cylinder around the x-axis. Or in the event where I take, y is my special coordinate, and I take my y-axis here, and I construct some cylinders in the x-z direction around this y-coordinate, or maybe some circles in the x-z direction around the y-coordinate, we get, a cylinder. Or similarly in the z direction, if I prefer to keep z fixed, and I draw some circles in the x and y directions, then we get a cylinder around the z-axis. So this is why they're called cylindrical coordinates. And here I've got an example of actually translating into cylindrical, which is really just taking a subset of 2 and 2 of the 3 of those and converting those to polar coordinates. Let's look at the same points we had before. So 3 halves, root 3 over 2, 1, 3 root 6 over 4, negative 3 root 6 over 4, negative 3 halves, and negative 5 root 2 over 4, negative 5 root 2 over 4, and 0. What are we going to do to convert to cylindrical? And in fact, I'm going to preserve the z variable in this case of cylindrical. That just means I'm going to, since I'm preserving z, I'm just going to circle the x and the y coordinates, and I'm going to convert each of these into polar coordinates. So each of these that I'm circling convert to polar. All right, so what does that look like? Well, all it looks like is we take the x and the y coordinate, and here we've converted them to polar, right? So this is square root of x squared plus y squared, and we take a tan 2 on the y and then the x. That's just going to give me root 3 and pi over 6. Meanwhile, the z coordinate is just coming along for the ride the whole time. We're just going to get that 1 for the z coordinate all the way through. In the second case, it's going to be the same. So I'm going to take the x and the y coordinates. I'm going to square both of them, add them together, take the square root for the radius, and I'm also taking a tan 2 of y and x. And meanwhile, the z coordinate is just coming along for the ride. So the z coordinate does not change at all. We get a radius of 3 root 3 over 2. And an angle of negative pi over 4, as well as that z variable that just came along for the ride. And in my last coordinate, I have the same. I take the x variable and the y variable, and I find their radius, which is just x squared plus y squared with a square root, and I look at the angle, so the a tan 2 of y comma x, and meanwhile the z variable 0 is just coming along for the ride. Turns out my radius here will be 5 halves. My angle is negative 3 pi over 4. So let's talk about graphing these. I mean, it shouldn't be too difficult to graph, because what we're actually doing is we're just doing polar coordinates, in this case in the xy plane, and then we're moving upwards or downwards in the z direction when we finish. So for something like root 3 pi over 6, as a polar coordinate, that would just be me going out root 3 amount, and then in the xy plane, an angle of pi over 6. But the fact that we've added 1 to the end means that right at the end of this, I go upwards by 1 unit, and I end up at my point. Or if I have my second point, which is 3 root 3 over 2, negative pi over 4, and negative 3 halves, well, I'm actually going out 3 root 3 over 2, which is about out there, and then negative pi over 4 is just within the xy plane, negative pi over 4, and then this final negative 3 halves is just in the z direction, so I'm going straight down in the z direction by negative 3 halves to the point I'm at. And then in the final case of 5 halves, negative 3 pi over 4, comma 0, I'm going to go out by 5 halves amount, and then I'm going to go within the xy plane an angle of negative 3 pi over 4. Because this last entry is 0, I'm not going anywhere in the z direction. But as before, if I look at the location of these 3 points, it's exactly geometrically equivalent to the location of the original 3 points considered as Cartesian coordinates. Of course, cylindrical coordinates have a volume form associated to them, but it is just the volume form of polar coordinates. Not really a surprise there. We just have a fancy new name for polar coordinates embedded in 3 dimensions. So the volume form is just going to be r as a multiplication of the regular volume form. Now, of course, when we preserve the x-axis, then the x survives. If you preserve the y-axis, the y survives. And if you preserve the z-axis, the z survives. But everything else becomes polar, so you pick up that multiplicative r in your volume form. Let's go ahead and look at some examples of cylindrical coordinates here. And you may ask, okay, which of the two variables should I choose to convert to polar? It should be pretty straightforward. I mean, look at this first omega. You can see x squared plus y squared here. That's probably the two you want to convert to polar. Convert to polar, since x squared plus y squared will just be r squared in polar. What does that mean? If you've already chosen x squared and y squared to be the ones that get converted to polar, then the z direction needs to be preserved. So our cylindrical case here will be that x squared plus y squared becomes r squared, and you're going to do the angle by doing a tan 2 of y over x. Okay, so how would we actually integrate this function, which is just xy, with respect to the domain omega given here? If we're going to convert to cylindrical, well, we're just going to replace every copy of x with r cosine theta because it is just polar, and every copy of y with r sine theta because it's just polar. So then f in cylindrical coordinates becomes r squared cosine theta sine theta. And then what happens to omega here? Well, we already decided that's going to be r squared. This is going to be kind of the funky little section right here. And here, because we'll have something like this x is actually going to become r cosine theta, is going to be less than this y, which will become r sine theta. So we'll have to figure out how to handle theta when we have that x and y relationship. Here that is, we've got 0 is less than r cosine theta is less than r sine theta. We also have this extra condition on y because we said y was greater than 0 in the original omega. How can we handle those? Start with 0 is less than r cosine theta is less than r sine theta. Well, r is already positive, so we can divide by r. That's not going to play a big deal, but 0 less than cosine theta less than sine theta. What about drawing a unit circle again and asking where on the unit circle is the x coordinate, right? So that's the x coordinate. Where is the x coordinate less than the y coordinate? Well, where would the x coordinate be equal to the y coordinate? That would be along this line, right? That would be along the line here and here. So where would x be less than y? Well, when x, which is left-right, is less than y, which is up-down, we want the leftness to be less than the upness. It's going to be everything to the left of these points. But we also have to consider that we required the y coordinate here, y coordinate, to be positive. And so the fact that we're requiring the y coordinate to be positive, we're actually going to force ourselves to be in this region. And finally, because we're requiring that the x-coordinate is positive, the x-coordinate needs to be positive here. The x-coordinate is only positive in this region. And so we do rely pretty heavily on the unit circle here, but we've recovered that theta can only be in that tiny little sliver, which is between pi over 4 and pi over 2. Okay, so then we've reduced, right? We've reduced omega from this collection of nonsense. There's so much stuff happening there, and we've used our unit circle to figure out what the bounds on theta should be. So we reduce that to say that actually theta is between pi over 4 and pi over 2, and because r squared was less than 1, we can say r is less than 1 as well. And of course, z has been coming along for the ride this whole time. Z is now between -1 and 1. And so our function, we're going to integrate this function, r squared cosine theta sine theta, over this domain, omega, which is r between 0 and 1, theta between pi over 4, pi over 2, and z between -1 and 1. We're going to integrate that function over that domain, and it's going to look like the following. We don't want to forget that we have our volume form in cylindrical coordinates. We just have to multiply by r with the volume form, and then here's our function f. So we take our function f, multiply by the volume form r, we get r cubed cosine theta sine theta. We're going to integrate in dr, d theta dz. The bounds on r are 0 to 1, theta are pi over 4 to pi over 2, and z is -1 to 1. What's that going to give me? Well, I just go through the motions of integrating now. It's really not that big of a deal to integrate this. What do I get as my answer? I get 1/8. Last example of cylindrical coordinates. Let's consider this function. The function of x, y, and z defined by x sine root y squared plus z squared. And you may be wondering again, what variables should I convert to polar? We're going to convert y comma z to polar because those are the ones that are showing up as the square root of things squared. In polar, that's just going to be the radius. And what do you know? It actually shows up in our domain omega as well. So if I go ahead and convert yz to polar, which is really converting to cylindrical where I'm preserving the x-axis, we just have that y is r cosine theta, z is r sine theta, which makes our function in cylindrical just x sine r. And what would it make omega in cylindrical? Well, it makes omega in cylindrical. I'm just replacing root y squared plus z squared with an r. And what do you know? Everything is already in a normal domain. We can just take care of theta as having this negative pi of pi. But here I've got f of r, theta, and x. And then don't forget my volume form r, right? Volume form in cylindrical is r, so I've got an extra r multiplying sign. That will force me to go through a little bit of integration by parts for the variable r. Of course, I'm integrating sine to get negative cosine there as well. The negatives canceled here. I'm going to integrate that cosine one more time to get a sine, evaluate at my r bounds. Lots of things simplified because it's sines and cosines of pi and 2 pi. And we just end up with negative 3 pi x. So negative 3 pi x. Integrate in theta. There's no variable theta sitting around, so that's just going to become a theta at 0 and 2 pi, so I'll get a 2 pi x. I'll get, really, when I integrate x squared over 2, but that's going to cancel with the 2 with the 2 pi, so I really just have negative 3 pi squared x squared, evaluate on my bounds for x, and I have negative 12 pi squared. So that gives you an idea of why sometimes you'll see domains where only 2 of the 3 variables have kind of square roots of squares added together, why you would want to use cylindrical coordinates to simplify everything. Anyway, that's what I've got. Hopefully you had fun with coordinate transformations. That's going to complete that section. I'll see you in the next one where we'll talk about really the 3-dimensional and 2-dimensional applications of the generalized Stokes theorem. So there's things called Green's theorem, divergence theorem, and the regular Stokes theorem. They're all very interesting. I'll see you in that one.